My name is Marco Chuki. I was a ball dropper and a height recorder.
My name is Alejandro Pufelis and I was the data recorder.
My name is Elidan Leonard and I was a videographer.
My name is Lucas Thomas and I recorded the angle.
Our time slot was January 22nd from 2 to 4 p.m.
Okay, so projectile motion is the motion in which an object travels when it's projected into the air.
Some instances where projectile motion is important is in sports such as basketball when trying to shoot the ball into the hoop.
Another instance where this is important is in regard to the military, when they decide when to launch missiles and where it's going to land and such.
Essentially, we used a Delrin ball with the steel plate, and we found our angle to basically maximize the length. After we found its length, we left the angle at 15 degrees in which we measured the maximum height. After we measured the maximum height, we just made sure that it cleared the obstacle.
We know that momentum is concerned along the line of impact. With a formula for the coefficient of restitution, we can find the relationship between the initial velocity and the final velocity with the given angles. So we get V1 sine beta over VO cosine theta, where beta is the angle of the bounce and theta is the angle of the inclined plane. We also know that momentum is concerned along the plane of contact. So VO sine theta will equal V1 cosine beta. Plug in one equation to another, we'll get a result for the angle of bounce, which will be beta equals tan negative 1 times e and cotangent theta. Previously, we found how to get the value of beta. With beta, we can get the value of alpha and plug it into our equation for maximum height. With the maximum height, we plug these variables into the equation and we turn out with this equation. As long as this equation fulfills the requirement of it being greater than the height of the obstacle, which is the vertical direction of the obstacle to a normal, we'll know that it cleared the obstacle in the vertical direction. To see if our bouncing ball cleared the object in the x direction, we'll use our x direction formula, which is our kinematic equation. We know that acceleration equals 0, so we can cross this term out. And we know that the time it takes is the y velocity over the gravity. We plug it into our time, and we know that when we multiply the final velocity in the x direction with the final velocity in the y direction, we'll get the final velocity squared times cosine alpha and sine alpha. We already calculated our values for alpha, which is beta minus theta. And when we plug those values in, we'll get our equation. As long as the result of this equation is greater than the x distance of the object, we'll know that it cleared it in the x direction. As long as these two equations respect the rules of it being greater than h obstacle and x obstacle, we'll know that the ball cleared the obstacles. We have the coefficients of restitution of both materials, for Durolin on steel and nylon on steel. We plug in the maximum heights for both materials into the equation and we solve for theta. This will give us different values for both of them. For Durolin, it's 14.91 degrees, which indicates the greatest angle at the slanted board can be at. And for nylon, it's 13.95 degrees. Putting the plate at these angles will give us the maximum height for which the ball will be able to clear the obstacle. When we plug in the values for theta into the equation, both answers give us an answer that's greater than 50.4, which means that they clear the obstacle in the x direction. Now we plug in 6.4 into the height of the object, and with the different coefficients of restitution for each material, and we find that the resultant theta is for Durolin 73.22 degrees and for nylon 69.38 degrees. When we plug the given values for theta into the x equation, we get that they are greater than or equal to 50.4 degrees, which means they cleared it in the x direction. With this, we get that our final results of range of the angles are these.
So our results for the Durolin ball on a steel plate were these values. We ended up with an alpha of 14.9 degrees, of a max height of h1 of 28.1 centimeters, an h of 6.4 centimeters, h naught was fixed at 49.5 centimeters, and the length L is 50.4 centimeters. For nylon on steel, these values did not vary. The only ones that changed were alpha, which changed to 14.8 degrees, and the max height H1 changed to 27.7 centimeters.
So out of these two combinations, the Durolin on steel had the maximum height at 28.1 centimeters.
Hmax was found experimentally. So we plugged that value back into the equation, which means that our experimental value and our theoretical value were both the same. In this experiment, we found that the higher the E value is between the materials, it results in a higher bounce, and that means that more energy is conserved. One source of error that affected us was when pulling out the metal rod to drop the ball, different velocities were used, which resulted in a different vertical velocity for the ball. One way to correct this would be by pulling the metal rod with a constant velocity. Another source of error were miscalculations.